Hi all. In the last class, we have discussed the existence of global parameterization and the characterization of that. C is connected if and only if it has a global parameterization. Now we have say theorem 2. Let C be a connected oriented plane curve, and let beta is equal to beta from I to C be a unit speed global parameterization of C. So we have already proved that there is a global parameterization if C is connected oriented plane curve, and if in the proof of the previous theorem, theorem 1, if you replace that x by norm x, then you will get the unit speed global parameterization instead of global parameterization. So if we consider such unit speed global parameterization, then this beta is such parameterization. We will prove that that parameterization is either 1 or periodic. So first we prove, and moreover we can get a characterization for periodicity as well. So first we assume that beta is not 1. Okay, beta is not 1. Then we can write this beta of T1 equal to beta of T2 for some T1 not equal to T2 belongs to these two quantities are in the domain of that beta. If this is the case, we will prove that this beta is periodic. We know that if we consider the unit speed parameterized curve as the maximal integral curve of this x, say this is our unit speed global parameterization, and alpha is the unit the integral curve of this vector field is the unit speed global parameterization. So alpha is the that integral curve. Then we have alpha of 0 equal to beta of T1, that is same as beta of T2. Okay, if this is the case, then we can write this beta of T is same as alpha of that T minus T1, because that alpha is the maximal integral curve, and this and that maximal integral curve coincides. This beta is also an integral curve. In fact, this is an integral curve. So maximal integral curve can be connected through this equation for some T1. T1 belongs to R. So we have this beta of T can be written as alpha of T1, and beta of T also can also be written as alpha of T minus T2, and we have this this is same as we will prove that this beta is periodic with the period tau is equal to T2 minus T1. That is because if you define this, then what is beta of T? From this equation, beta of T is equal to alpha of T minus T1, and we will replace T minus T1 from this. When you write this, then what is T minus, when you add T on both sides, you can get T plus tau equal to T plus T2 minus T1. Okay, so this implies what is T minus T1? T minus T1 is equal to T plus tau minus T2 by transposing this T2 to the left. So we replace T minus T1 with this equation. That is same as alpha of T plus tau minus that T2. But we already know that this alpha of something minus T2 is same as beta of T. So this is same as beta of T plus tau. So which shows that beta is periodic, because beta of T is equal to beta of T plus tau. So this proves the first part, beta is either 1 or periodic. That means beta is not 1, then we got beta is periodic. Now we will prove the moreover part. Beta is periodic if and only if that C is compact. So for that we first assume that we need to prove that beta is periodic if and only if C is compact. Okay, so first we assume beta is we will prove two implications separately. So first of all, we will assume this beta is periodic. Okay, then we know that since this beta is a global parameterization, so beta of I is equal to C. So this is the ontoness of the global parameterization. So beta is periodic means beta of suppose beta is periodic with the period tau. So we have point T naught and T naught plus tau. Okay, beta assumes all the values in between this as same as beta of I. So this is same as beta of I, that is equal to C. Okay, so but we know that this beta of this interval, okay, this is the compact interval. So C can be considered as the image of the compact interval. Okay, under beta, this beta is always a continuous function. So continuous image of a compact set is compact, then this C is a compact set. Okay, C is compact. That means whenever we assume beta is periodic, then C is compact. Conversely, we assume we will prove that this is in fact P implies Q, and we will prove that not P implies not Q. Okay, that will lead to Q implies P as well. So we assume beta is not periodic. Okay, we will prove that this C is not compact. If beta is not periodic, by previous part we can get this beta is 1 1. Okay, beta is 1 1 means suppose we have a plane curve, this is our C, then we know that beta is from I to, this is our interval I, suppose this is our interval I, and beta is from I to C. Okay, this is an onto function, then this is an onto function, and we have, if we assume beta is not periodic, then we can get this beta is 1 1. Then you can define this beta is 1 1 onto function to the C, then you can define beta inverse. So beta inverse is from C to I, which is contained in R. Is an open interval in this case. So I is an open interval, and if we assume beta is not periodic, we will prove that this beta inverse, consequently this is a continuous function from, we will prove the continuity of this beta inverse. So we will get a continuous function beta inverse from C to I, which does not assume a maximum. Okay, so because this beta inverse is a function from this C to the open interval, okay, and beta is not periodic, then this beta inverse is a function from C to this I. Okay, so once you prove this beta inverse is a continuous function, then beta inverse is a onto continuous map from C to I. Therefore, this beta inverse does not attain maximum on this interval because it's an open interval. Clear? So this C cannot be compact. Okay, if C were compact, then this beta would have been beta will have a maximum value on the C. Okay, so we know that since this I is an open interval, there is no maximum for beta inverse. So it is only it remains only to prove that this beta inverse is continuous. Okay, so in order to prove beta inverse is continuous, we start with a suppose we will take a point T naught here and an open interval containing T naught. Clear? So for any point T naught and open interval, there exists a point here, and which is continuous. That would implies a domain here, or at the point P naught we have an open interval, open rectangle. Here we will construct an open rectangle, same as using the method described in the theorem 1, such that this C intersection B is always contained in this that interval we have selected here. So if T belongs to this P belongs to this, we will prove that beta inverse of P in this interval. So I call that interval as some that minus T naught is less than some epsilon. Okay, we will prove that if this is the epsilon interval, then corresponding to this interval we will find an open set here, and if we choose any P here, then P in this curve in this open set C intersection B, we have this beta inverse P minus T naught. This T naught is nothing but beta inverse of P naught. Okay, so beta inverse of P naught which is less than epsilon. This is what we have to prove. Okay, so, to the continuity. Now to prove this, we start with a T naught. T naught belongs to I and an interval. To select an interval, we choose epsilon greater than 0 and we define the interval as mod T or mod T less than epsilon and we represent the points in that interval as T plus T naught. So when mod T less than epsilon, then we can get this values over this interval and that is in I. Okay, choose all such T and gamma of T is equal to beta of T plus T naught. We set gamma of T is equal to beta of T plus T naught for T such that mod T less than epsilon. Okay, so we set this is the gamma of T, or we define gamma of T in this manner. Choose an open interval, open rectangle, same as in the previous theorem, with the open rectangle B such that P naught is equal to beta of T naught, that is equal to gamma of 0. Okay, this is same as in the proof of theorem 1. Okay, now we have C intersection. You can easily construct B such that C intersection B is contained in image gamma. Okay, so this is in the image gamma means we have modulus of this beta inverse of P. We need to prove that beta inverse of P minus beta inverse of that P naught. We define P naught is equal to beta of T naught. So beta inverse of P naught is equal to T naught. So we will prove that this is always less than epsilon. So this is same as beta inverse of P minus beta inverse of P naught is equal to T naught, and which is in the image gamma. So this is modulus of gamma inverse of P. Okay. This is because we already set this gamma of T is equal to this one. I call that is P, gamma of T, which is equal to beta of T plus T naught. Okay, now what is gamma inverse of P here? Gamma inverse of P is equal to T, that is the gamma inverse of this quantity is equal to T minus T naught. So this is same as beta inverse T plus T naught. Okay, sorry, beta inverse of P naught as well. So this is beta inverse of P, and beta inverse of P is nothing but T plus T naught. Now we write this gamma inverse P is same as beta inverse of P. Beta inverse of P this is not gamma inverse. We write that is, from this we consider this as two equations. P is equal to gamma of T and P is equal to beta of T plus T naught, and from this you can write beta inverse of P equal to T plus T naught. Then that implies beta inverse of P minus T naught, that is same as T, and from this you can write T is equal to gamma inverse of P. So we replace this by gamma inverse of P. That's why here we write modulus of beta inverse of P minus T naught is same as modulus of gamma inverse of P. And we know that in the definition of gamma, this T comes from T satisfies this condition. Okay, this mod T is less than epsilon. So this modulus of this is same as modulus of beta inverse P minus T naught is same as modulus of T, that is same as modulus of gamma inverse P. So this is same as modulus of T, which is less than epsilon, that comes from this. So whenever we have this T naught here, then we have beta inverse of we can get an open interval here. If from this you can select a P, beta inverse of P minus beta inverse of P naught is less than epsilon. Okay, for any epsilon greater than 0, there exists an open set here such that beta inverse P minus beta inverse of P naught less than epsilon. So if you choose any T naught in this interval, you can prove the continuity of this beta inverse using this manner. That means beta inverse is continuous map from a set C to this I, this open interval I, which is onto. Therefore, this beta inverse does not attain maximum or neither maximum nor minimum. Therefore, this C cannot be compact. Therefore, C is not compact. That means if beta is not periodic, then C is not compact. Beta is periodic, then C is compact. So which shows that beta is periodic if and only if C is compact. So this proves the theorem 2.